So I've taught you that objects in free fall near the Earth, if we ignore air resistance, I added a whole bunch of conditions there, they accelerate at 9.8 meters per second squared. Why? Well, it's because the Earth has a gravitational field strength of 9.8 newtons per kilogram. What do I measure newtons in? What do I measure in newtons? What do I measure in kilograms? What is force divided by mass? What's F over m? It's acceleration. This is an acceleration. This is another way to write acceleration. The reason objects in free fall accelerate at 9.8 meters per second squared is because the gravitational force pulling on them pulls on them with 9.8 newtons of force for every kilogram of mass that they have. Not a coincidence that those are the same numbers. It's because they're both accelerations, different ways to write them. So up until now, we've been aware of two ways to determine the gravitational field of a planet. The first way, you can measure it by measuring the free fall acceleration. We can drop something. We kind of tried to do that in Physics 11 when you dropped objects from the ceiling and timed them, and you were hoping to get 9.8. If you did that with good equipment, Zach, in a vacuum with electric eyes and computer timers, you would get 9.8. Negative if you wanted to call it down, but you would get a magnitude of 9.8. That's one way. There's a second way as well. So we can drop an object in a vacuum and time its free fall, but we can also measure the gravity field at a location by measuring the weight, the mg, of a small test mass, little m. The ratio of weight to kilograms gives the gravity field. Remember, if Fg equals mg, get the g by itself. Okay? So let me show you what I mean by that. Pause the video for a second. So the second method is hang a mass from a force Newton scale and go weight, mg, divided by that mass, and that'll give you little g as well. So what I want you to realize, first of all, is another way to say the acceleration due to gravity is the gravitational field strength. That's really what this one here is. How many newtons of force are being pulled on every kilogram? And it's measured in newtons per kilogram, which must be the same as acceleration, meters per second squared, because F equals what? ma, get the a by itself. And so the question we've asked is, how can we figure out the gravitational field strength, little g, on the moon or Mars or other planets, or, you know what, universally, anywhere? So here's what Isaac Newton found in his experiments. He found that universal gravitational field strength depended on two things. It depended on the mass of the object that was creating the gravitational field, the mass of the planet, the mass of the star, the mass of the moon, the mass of the asteroid. And he noticed that it was the reciprocal, I wrote this wrong, the square, I apologize, of the distance from the center of the object or the planet, except the squared was on the bottom. It was a reciprocal. It was 1 over r squared. It depended on m on the top and 1 over r squared. The r squared is on the bottom. In other words, he found that universal gravitational field, little g, is proportional to, there's a symbol for is proportional to, and it's a little fish. The mass of the planet causing the gravitational field divided by the square of your distance from the center of that planet. Problem. I want gravitational field to be in newtons per kilogram. This would be in kilograms per meter squared. The units don't match. So he said we need a conversion factor. In the same way that if you want to go from minutes to hours, you times by 60 to get hours. In the same way if you want to go from Fahrenheit to Celsius, there's a conversion factor. In the same way if you want to go from meters per second to kilometers per hour, the conversion factor is 3.6. There is a conversion factor. But he couldn't find it. So he put a placeholder in. He said universal gravitational field, leave a space, big M over R squared. And he said the conversion factor, he put a capital G there. He called that the gravitational constant of the universe. That will be the conversion factor. But it was so small, he couldn't measure it. Because gravity is weak. It's very weak. So what he did is he set up all of his equations so that big G would cancel out. And you could do that for a lot of applications with some cleverness. Okay? What is big G? It's 6.67 times 10 to the negative 11. Times 10 to the what? It's 0.00000000667. It's small. It's very small. And it's on your formula sheet. On the same page as I have all the radiuses and masses of the planets, somewhere there you should see big G is 6.67 times 10 to the negative 11. You'll probably end up memorizing it during this unit, but you might not have it memorized for the whole year. You just get sick of looking it up. It's not that convenient a number page. It's kind of messy, 6.67 times 10 to the 11. It's the universe, sorry. What is big M? Big M is the mass of the planet, or star, or moon, whatever is sending out the gravitational field. R squared, that's the square of your distance from the center of the planet. Some textbooks will write this. Instead of R, they'll use a D for distance, but you're going to see in a few days why I'm using R, because we're going to bring in some circular motion and gravitation stuff in. Notice how small big G is. This is because the force of gravity is by far the smallest of the four fundamental forces in the universe. So Newton predicted the need for that conversion factor, but it was just so small he couldn't come up with an experiment to measure it. So he set up his equations so that big G would cancel. About 100 years after Newton published his gravitational equation, Henry Cavendish measured G in 1798. How the heck would you measure something that small with 1798, 1800s technology? It was very, very clever. Put your pencils down, look up. I'm going to mute the video because it's got disco music in the background, which is just loud and annoying. But someone has done a basic recreation of it. Where is it, Mr. Duick? Here we go. Cavendish experiment. What he did is he used a beam of wood and he put a couple of lead weights on the end and he suspended them from strings. Now this video is from 1999. You can't see that there's fishing wire, but there is fishing wire right there and right there. So it's suspended and it's able to twist very, very easily. That's step one. Here's a modern version using styrofoam instead of wood. Top bar is suspended by a fishing line. It's hung from the top of the ladder. It's hard to see in the video. But again, the key idea, this bar is able to twist very, very easily. Cavendish did, next to each of the little lead weights, he put a really big mass right there and right there. Like he used big barrels of dirt. These are lead bricks. Do they have mass? Everybody say yes. So will they send out a gravitational field? A tiny one, but yes. So this brick here will tug ever so slightly on that mass and pull it towards it. This brick here will tug ever so slightly on that mass and pull it towards it. And Cavendish left this experiment alone in a room, allowed the rope to slowly twist, and by measuring how much the rope twisted, he knew the twist force on the rope very accurately, and so he was able to say F twist equals FG, and he was able to get the big G by itself and solve. Watch. Takes a while, this is sped up, but you'll see very slowly the bar is twisting, the bar is moving, gravity is working. And then this experimenter decided to reverse it, so put the bricks on the other side. And again, speeding it up, but still one continuous drop, just time lapse. It's that. So that's the Cavendish experiment. In my mind, on the top 10 list, that was a very clever experiment. And lo and behold, Henry Cavendish now knew that G was 6.67 times 10 to the negative 11. He was a little bit off, but he was close. So what was the first thing that he did? He said, I can finally calculate the mass of the Earth. Up until then, the way they had estimated the mass of the Earth, and this is true, they had taken just a bunch of shovels of Earth, weighed those, taken an average shovelful mass, and then basically said, well, how many shovelfuls make up the volume of the Earth? We'll multiply. Okay? Cavendish said, now I can do better. He said, okay, I know that little g is equal to big G, big M, over r squared. He knew little g was 9.8. The radius of the Earth, we've known for a long time. Eratosthenes, a Greek mathematician in around 300 BCE, actually came up with a clever experiment and got the radius of the Earth within about 5%, and we got better and better. So the radius of the Earth we knew. Big G he had just calculated. Get the M by itself. How? Dartmouth, how? And times by? Yep, he did this. By hand, without a calculator. Took him a while. Little g, r squared, over big G. So little g was 9.8. R from your formula sheet was 6.38. Times 10 to the 6th. Don't forget the squared. All over 6.67 times 10 to the negative 11. What do you get? And Cavendish was carefully calculating this by hand. And when he got an answer, he sat back. First of all, I would imagine there would be a little bit of awe and wonder. I'm the first person who actually knows the mass of my planet. But also, Danica, what'd you get? Okay, this is my way of saying, by the way, all of you want to practice typing this in because you want to become familiar with how do I type that 6.67 times 10 to the negative 11 on my calculator. Some of your scientific calculators might have this number programmed in as a constant. Go ahead and use it if you do. I think you're going to get around 5.98 times 10 to the 24th. Think you made a typo if you didn't get that. Should be 5.98 times 10 to the 24th. Double check to make sure you did 6.67. Didn't miss a decimal there. Times 10 to the negative 11. It's 5.98 times 10 to the 24th, yes? That, which is the mass of the Earth. And Cavendish looked at this and went, wow. Because that number was way too big. It was far larger than the estimate with shovels full of dirt. That there was the first hint that it's not dirt all the way down. We now believe that as you go further and further down, what do we believe is at the very center of our Earth? A very dense iron core. That's what also gives the Earth its magnetic field. That's why compasses and things work. This right here was the first hint that, yeah, it's not rock all the way through. It's way too big, way bigger than their previous value. Every planet has its own gravitational field strength. You've memorized G on Earth. What's little g on the Earth? By the way, don't confuse little g, which is the gravitational field strength, with big G. Big G is a constant. It's always 6.67 times 10 to the negative 11, anywhere, even near a black hole. What's little g on the Earth? 9.8. Was that a hand-up question? Yeah.
I have a dumb question.
Earth can't get heavier, right? That's a good question, not a dumb question. Is the Earth gaining mass? I know we're losing helium all the time. Helium is an inert gas. It doesn't bond with other things. We find it underground in pockets, but anytime you have a helium balloon, if you let it go, that helium will eventually work its way up and escape Earth's atmosphere and end up in outer space in the vacuum of space, never to return to Earth. So you could make an argument that Earth is probably losing some degree of mass on a very small level, I think. But we're also absorbing solar radiation and solar particles. That's a good question, actually. That's a better question than you realize. I'll have to do some digging. Back to my question. What's Earth's gravitational field strength? You all know this? 9.8. What about on the moon? It's about 1.6. Physicists put together a nice video. This is dropping a 1 kilometer ball for 1 kilometer on a bunch of solar system bodies. And this is accurate and to scale. The sun, let's start over, has a very strong gravitational field strength. Its gravitational field strength, Gabor, can you read? You're at the front. What's its gravitational field strength for the sun? 274. Mercury, 3.7. Venus and Earth, very, very close. If Venus wasn't such a nightmare runaway greenhouse gas, that would be the planet that we would be trying to get to. Far better for us to live on than Mars, except for the fact that it's so hot, lead melts. The Russians landed a probe on Venus in the mid-70s, and they managed to keep it alive, I think, for about 12 minutes, which was an extraordinary feat of engineering. We do have a couple of pictures that made it out of there, but it just melts pretty quickly. If we could deal with that, Venus would be the planet to terraform. But we don't have the technology to do that. Earth, 9.8, Moon, 1.6. Well, here we go. So there's the sun. Letting it drop for 1 kilometer. Jupiter, about 24.8. Interestingly, how come Saturn has a gravitational field strength very similar to the Earth? Isn't it so much bigger? It's very less dense. In fact, Saturn would float on your bathtub. It floats on water. It's that undense. What's the opposite of dense? Can't think of the word. I'm sure there is one. Mars and Mercury, about the same. And then we have the Moon. Pluto, not a planet. Get over it. And Ceres. By the way, one of the reasons that Pluto was demoted from planetdom is an argument was being made that Ceres should be a planet. We'd found 4 or 5 other large asteroids past Pluto that were as large as Pluto. So it was either cap it at 8 or up it to 13, 14. What if we find more? So. An interesting question. If you were an astronaut and you landed on Ceres, could you launch yourself into orbit by jumping? I'm not sure. I'd have to run some numbers. It's a pretty small gravitational field. I wonder if you'd be able to achieve escape velocity just with your legs. It's a good question. There you go. So, we have said, we got a choice. I can pause here and pick this up tomorrow, or I might be able to get through the whole lesson today and make tomorrow marking the quiz and then the rest of the class a work period. What would you prefer? Splitting the lesson up in two, giving you half an hour to work now and half an hour to work tomorrow? Okay, Danica nodded, so we're going to pause here. So we have universal gravitational field, big G, big M over R squared. Then we'll get the universal law of gravitation tomorrow.
Mr. I tried to get